Okay, so I'm going to try to finish 16.3, what I wasn't able to get to yesterday, and most of this is essentially just going to be some example problems. So here is 16.2, and this is in the PowerPoint. We are given the length of a vibrating string to be 2.5 meters, and we're given that it vibrates at some sort of frequency of 100 hertz. And it has a node at 1 meter and 2 meters. At 1 meter and 1.5 meters from one end of the string. And no points in between those two. Which harmonic is this? What is the string's fundamental frequency? So that's F1. And what is the speed of the traveling wave? Alright, so this diagram kind of gives it away, but we were only given this information here. Okay, nodes are always going to be equally spaced. Alright, so if this is 2.5 meters, and there's one at 1 and 1.5, the only way that can be possible is if there is a total of 6 nodes, with them being a half a meter apart, just like how they are here. They're a half a meter apart. So this is node 3, 4, 5, 6. So if I have 6 nodes, that means I must have 5 antinodes. So here we have 1, 2, 3, 4, 5. So we know this is the 5th harmonic. So that's the first part. Okay. Alright, what is the string's fundamental frequency? So if it is the 5th harmonic, therefore 100 hertz is equal to F5. So that's the frequency of the 5th harmonic. Alright, so remember that F5 is equal to the mode number times F of 1. So the mode number here is 5, and we're looking for F1. So divide by 5, and we get the fundamental frequency to be 20 hertz. The next part is, what is the speed of the traveling wave on the string? So we're looking for the speed. There's kind of two ways we can do this. So for the speed, we don't know anything about the tension here. Alright, so if there's no information given to you that you can find the tension, then you're going to have to use the wave equation, which is this. Okay, so we need to use this information. We know the frequency. We can find it with F1 or F of 5. Okay, but in order to do that, we're going to need to find the wavelength. So in order to find this, we can do either the wavelength of the first node times the frequency of the first node, or we're going to get the same answer, so I'll do it both ways. So first we need to find what the wavelength is going to be. Okay, so remember this formula. It's 2L over the mode number. So the mode number is 1, so the wavelength is 2L. Okay, so this is 2 times 2.5 meters, which is 5 meters. So according to that, 5 meters times 20 hertz, we get 100 meters per second. Or if we find the wavelength here, 2L over 5. So 2 times 2.5 meters over 5. Okay, let's see. And that comes out to be just 1 meter. So then the velocity is 1 meter times 100 hertz. It's equal to 100 meters per second. Okay, so we get the correct answer there for both of them. Okay, so this next example involves a guitar, which is a stringed instrument. And very importantly, that the frequencies that we hear from instruments are going to be the fundamental frequency. Right? So it will form a standing wave, but it's going to be just the first mode number. Right? You're not going to see a guitar string with 2, 3, 4 antinodes or anything like that. Right? It'll just be one that forms. So this information here shows that this 110 hertz is our fundamental frequency. Okay, stretched between two fixed points. So that is our length. And this is the mass of the string. Right? So it is made out of usually metal, so I guess we cannot really ignore the mass as much as we could if it was nylon or something. And we're looking for the tension here. All right, so since we're given the mass of the string, one of the first things that we're going to want to do is to find the linear density. So that's the ratio of the mass of the string over the length of the string, and the mass was 2.86 grams. So this is usually how I kind of will write things sometimes. This is 2.86 grams, and to go from grams to kilograms, right, it's -3. So that easily converts it to kilograms. And then the length of the string was given to be 0.64 meters. So this gets us our linear density of 4.47 times 10 to the -3. In our units, it's mass over length, so kilograms per meter. All right, so now we can find the frequency. So for this, we're really going to, I'm going to start once again from the wave equation. So we're going to start from the wave equation, which remember is this. So the velocity of the wave times the wavelength of the mode and the frequency of the mode. Alright, and so since we're talking about a string, this is tension over our linear density. And you might remember that the mode, the wavelength in general is going to be 2L over M. So if we're talking about a musical instrument, this is just 2L. And then we have our fundamental frequency. Okay, so we're going to solve for tension. So we're going to square both sides. Okay. And I don't feel like expanding this right now. So then the tension is going to equal mu times 2L F1 squared. So tension is 4.47 times 10 to the minus 3, I believe. Yep. Kilograms per meter times 2 times 0.64 meters. And then our frequency, which was 110. Okay. And this comes out to be about 88.6 newtons, which is a fair amount of tension. Okay, so this is the problem that really made me want to do this video, because it relates a lot into the demonstration that we did. So we're given two different strings with the same linear density. Okay, let's watch out for units here. So this is 5 times 10 to the minus 3 kilograms per meter. We're given the length. Here is a half a meter. Let's be careful. And the block is attached to a string of mass 20 kilograms. So the mass is going to be important here because that will allow us to find tension, because the tension is going to be mg. Okay, but we do not know the mass of m. Okay, so some notes that we need to have is that this, right, this is, we have only one antinode, so our mode number is 1. Here our mode number is equal to 3. Okay, so what is the driving frequency? So this tells us the frequency. This is that second possibility where the frequency is constant. The frequency is going to be constant for these, but the tension is going to change. So you might remember the derivation that I did on the board yesterday where we wrote that the mode number is going to be proportional to 1 over the square root of tension. And so this, since we know the mass is going to be mg, but we're still looking for the frequency here. So let's, as always, let's kind of start from the wave equation that kind of is going to help us. Right. And then the frequency. So that's what we're looking for. We don't know what this frequency is. That's what we want to solve for. And so since it is a string, it's the tension over the linear density. Luckily, we were given both of these. Right, so that's good information to know. So we know both of these. And then the wavelength. Well, we were given that it is mode 1. So that means that the wavelength is going to be 2L. And then the frequency. Okay, so now we can look to solve the frequency because we were also given what the length is. Okay, and we can find the tension, but we'll do that later. So we're gonna square both sides, just like how we did last time.
When is the presentation due?
Okay, so that gives us t over mu on the left-hand side.
Do you know when
And we'll just kind of go ahead and split this up since we're going to have to anyway. Okay, so we're looking for the frequency. Alright, so that will give us, so now let's go ahead and divide by 4L squared. On both sides, divide by 4L squared. Okay, so now we have T over 4 mu L squared is equal to frequency. So then the square root T's is going to equal to F. And remember that tension is just going to be mg. Okay. Alright. So we should be at the point now where we can plug in our values. Okay, so 20 kilograms, 9.8. Over 4, and the linear mass density was 5 times 10 to the minus 3. And the length was just 1/2 meter. Alright, so the frequency comes out to almost exactly 198 hertz. My assumption is that if you used 10 for G instead of 9.8, it would have probably come out to be exactly 200 hertz. Right, so that is the frequency. Now the next thing we're looking for is the mass. Okay, so now we're at node 3. Okay, and so this is going to be when I'm going to want to use this proportionality that we used before, where the mode number is proportional to the square root of tension, which would also be but then G is another constant. So essentially we get a proportionality that the mode number is proportional to 1 over the square root of the mass. So what this means is if we want to increase this by 3, then in order to increase the mode number by 3, we would have to decrease the mass by 9. Okay, so let's show that, because if we do 1 over, right? So if we do this, right? So the square root of 1/9 is 1/3, and then if we're dividing by that, if we're dividing by 1/3, we get 3. Okay, so what that means is for node 3 that the mass is going to equal 1/9 of 20 kilograms, which comes out to be 2.22 kilograms.